All right, welcome to another deep dive. Today we're going to get into something pretty interesting.
Yeah.
It's a bit of a philosophical puzzle that's kind of wrapped up in math.
Oh, okay.
It's the idea of circularity.
Circularity.
So
Interesting.
we're talking about like when things are defined in terms of themselves
I see.
and, circular, this can be a tricky thing, right?
Right. Yeah, you can get into these sort of vicious circles, but
It's
then
got
sometimes it seems like maybe circularity is pointing to something deeper, like some self-sustaining kind of structure.
Yeah, and that's exactly the tension that we're going to explore today.
I'm excited.
Okay, so to really kind of dive into this, we're going to focus on what's called non-well-founded set theory.
Okay.
And essentially what this is about is the possibility of sets that can contain themselves.
Okay.
Like imagine a set called S,
Uh-huh.
and S is an element within S.
Oh, wow.
So it's like this self-containing idea.
Yeah.
And this is what's called object circularity. And it really kind of messes with our standard ideas about what a collection can be.
Yeah, for sure. I mean, like, just thinking about it that way, it's like, wait a minute. That
Yeah.
can't be, right?
It's not how we usually think about it.
Exactly. Yeah.
And what's really interesting is that the standard framework for most of math is called Zermelo-Fraenkel set theory,
Right. ZFC.
right? ZFC.
Yeah.
And it has an axiom built into it called the axiom of foundation
Right.
that explicitly says you can't have these self-containing sets.
It rules it out right from the start.
It says no way, no how.
Yeah, it's like one of the foundational things you just can't do.
Right. It's like saying there's no infinite regress of membership.
Okay.
So like you think about your ancestry,
Mm-hmm.
you know, you always find distinct individuals when you trace it back.
Right.
The axiom of foundation says the same thing about sets.
Okay. So it's got to bottom out somewhere.
Yeah, you can't just keep going forever in a loop.
Yeah.
So this leads to the question, like, why would anyone want to challenge this principle?
Yeah. I mean, it seems so fundamental to how we think about sets.
It's like we're questioning the bedrock of math.
Totally.
But there's a reason.
Okay, tell me.
And that reason is the anti-foundation axiom,
Oh,
or AFA.
all right. AFA.
So this was pioneered by mathematicians like Forty and Hansel,
Okay.
and really championed by Peter Axel.
Right.
And AFA basically says, what sets can contain themselves?
So it's going completely against that axiom of foundation.
It's like throwing it out.
Yeah.
And not only that, it says you can have these infinite descending chains of membership.
Okay. So you can just keep going down and down and down.
It's like a recursive loop forever.
Yeah.
Total shift from how we normally think about sets.
Totally. And it kind of reminds me of like those philosophical debates about foundationalism.
Yeah.
On the one hand, you've got this desire for a very strict system built up from the bottom.
Right.
Like everything has to be grounded in these well-defined elements. And that's kind of like the axiom of foundation. But then there's this other view that's a little more loosey-goosey.
Yeah, more flexible.
More flexible. Yeah, it's like, okay, maybe self-reference and circularity are fine as long as they make sense in the system.
Right.
And AFA is definitely in that camp.
Yeah, it's like maybe our foundation shouldn't exclude these circular structures.
Exactly.
And the motivation here isn't just to cause trouble in math.
Right.
There are real-world phenomena that seem inherently circular.
That's true.
Like think about game theory.
Yeah.
Like player A's strategy depends on what they think player B will do.
Mm-hmm.
But player B's strategy depends on what they think player A thinks.
Oh, wow. So it's like a loop.
It's a loop.
Yeah.
And standard set theory has to kind of break down these layers of beliefs to model this.
Right.
But AFA says you can just represent it directly with the circularity.
Oh, okay. That makes sense.
And it's not just game theory.
What else?
Think about language,
Okay.
how we define words.
Right.
Sometimes a definition will circle back to the term it's defining.
Yeah, I can see that.
Or in computer science,
Okay.
you have things like situation theory or the calculus of communicating systems,
Yeah.
where you get these circular dependencies naturally.
Interesting.
So AFA gives us a way to model all this stuff without having to get rid of the circularity.
Okay, so it's like it's giving us a more powerful tool.
Exactly. It's a way to represent the world more directly.
Yeah. And it's interesting to think about, if the world we're trying to model has these circular aspects,
Yeah.
shouldn't our math be able to handle that?
Right. Like, why force everything to be non-circular if reality isn't?
Exactly.
So in this deep dive, we're going to really explore what happens when we accept AFA.
I'm ready.
How does it change how we think about sets?
Right.
What are the consequences of having these self-referential objects?
Yeah.
And how does all this connect to bigger philosophical questions about the foundations of math?
Right. Are we stuck with this bottom-up way of thinking, or can we be more flexible?
Yeah, exactly.
All right. Well, let's get into it.
Okay, so we've been talking about object circularity,
Uh-huh.
but there's also this idea of definition circularity,
Okay.
which is where we define a collection in terms of itself.
Right.
So can we unpack that a bit?
Yeah, I think that's an important distinction to make,
Right?
especially for people who are, really into the details of language and definitions. It's
Yeah.
really crucial to see the difference between the two.
Absolutely. So the key difference is whether the self-reference is in the object itself
Okay.
or in the description of the collection.
Right.
So like think about this equation. X equals 1/2 x plus 1.
Oh, okay.
It's a circular definition.
Uh-huh.
We're defining x using x in the expression,
Right.
but it's totally fine.
Yeah, it just means x equals 2.
Right, we get a clear answer.
Exactly. The circularity is resolved,
Yeah.
and you end up with a normal number.
Right.
But now let's contrast that with a set.
Okay.
Let's say set X is equal to the set containing only X.
So x equals the set of x.
Yeah. So here, the object itself is circular.
Right. It's a member of itself.
Yeah.
And that's what standard set theory with the axiom of foundation says is a no-no.
Right. It says you can't have that.
And that's exactly what we're focusing on today.
Okay, so this object circularity.
Exactly. And we're going to use AFA to really examine it.
All right.
So to make this a little more concrete,
Yeah.
there's this example of streams of numbers.
Okay. I've heard of streams.
Could you explain that?
Yeah. So think of a stream as an ordered pair.
Okay.
The first element is a number, we call it the head.
Uh-huh.
And the second element is another stream called the tail.
So it's like a sequence?
It's like a sequence, yeah.
Okay.
And this lets you have circularity because you could have a stream S where the head is 0 and the tail is S itself.
So S equals 0, comma S.
Right.
Okay.
And if you keep going with that, you get 0, 0, 0, 0 forever.
You get an infinite sequence of zeros.
Exactly.
Okay. But here's the thing. In standard set theory, that kind of stream wouldn't be allowed.
Because of the axiom of foundation.
Exactly.
Yeah.
So you have to kind of cheat.
What do you mean?
You have to reduce them to functions.
Okay.
So instead of having that self-referential stream, you have a function that takes a natural number and gives you back a number.
Okay.
So in this case, the function would always output 0.
Right. No matter what you put in, you get 0.
And there's a way to go back and forth between these two representations.
Okay.
But the question is, does that reduction really capture the whole idea?
Yeah, is it losing something?
It's like translating poetry into another language.
Right. You might get the meaning, but the feeling is gone.
Exactly. It's not quite the same.
Yeah.
And the source actually mentions this operation called zip.
Zip? What is that?
So it takes two streams and interleaves them.
Oh, okay. So like if you had 1, 2, 3, and 4, 5, 6,
Yeah,
you'd get 1, 4, 2, 5, 3, 6.
exactly. And the definition of zip is really easy when you think about streams directly. But if you try to do it with functions, it gets messy.
So it's like the direct way is more elegant.
Yeah, it just makes more sense.
I see.
And then you can get into systems of equations that define streams.
Okay.
Like imagine x equals 0, comma y.
Uh-huh.
Y equals 1, comma z.
Okay.
Z equals 2, comma x.
So they're all kind of referring to each other.
It's a loop.
Yeah.
And AFA says you can just treat those as streams directly.
Okay.
You don't have to find some function to represent them.
That's nice.
It's much more straightforward.
Yeah. I'm starting to see the appeal of AFA.
And you can even have systems that use zip.
Oh, wow.
Like x equals 1, comma zip xy.
Okay.
Y equals 0, comma zip yx.
And what happens there?
You get these crazy sequences like the Thue-Morse sequence.
I've heard of that.
And AFA just handles it all naturally.
That's pretty cool.
So it's like it's giving us a more powerful way to work with these circular definitions.
Yeah, it's not afraid of the circularity.
Exactly.
All right, so we've talked about streams. What else is there?
Well, the source also talks about infinite trees.
Trees. Okay.
And it's kind of similar to streams.
How so?
You can define them recursively.
Okay.
So you start with some basic building blocks,
Uh-huh.
and then you have rules for combining them.
Right.
And you can even have a tree be defined in terms of itself.
Okay, so like a subtree of a tree is the tree itself.
Exactly.
Wow.
And the source talks about defining the set of all trees,
Okay.
which they call T.
Oh, tree.
And they give an equation for it that includes tree R on both sides.
So it's self-referential.
Exactly.
Okay.
But here's the kicker.
What?
Standard set theory says that set can't exist
Why not?
because of the axiom of the foundation.
Oh, right.
It says you can't have that kind of self-reference.
So it's like our intuition about these trees is wrong.
In a way, yeah.
That's weird.
But AFA says, fine.
What does it say?
It says those sets can exist.
Okay.
It allows for these non-well-founded sets.
The ones that can contain themselves.
Exactly.
So AFA is like opening up this whole new world of sets.
It's like expanding our mathematical universe.
Yeah.
Where self-reference isn't a paradox.
But the feature.
Exactly.
That's pretty mind-blowing.
So we're really starting to see how AFA challenges our standard intuitions.
Yeah, it's making me rethink what sets can even be.
And the source goes even further.
How so?
They introduce this idea of hypersets.
Hypersets, okay.
Which are also called non-wellfounded sets.
Right.
And they use this concept of graph decorations to explain it.
Graph decorations, what are those?
So this is where it gets really interesting.
Okay, I'm listening.
Imagine you represent sets as graphs.
Okay, like a network diagram.
Exactly. And the arrows in the graph show membership.
Okay, so if set A contains set B,
yeah,
there's an arrow from A to B.
Right.
Okay, I can visualize that.
And then a decoration is a way to assign a set to each node.
Okay.
But in a special way.
How so?
The set you assign to a node has to be exactly the set of decorations of its children.
Okay, the nodes it points to.
So like if a node has 2 children and those children are decorated with the sets 1 and 2.
Okay.
Then that node has to be decorated with the set containing 1 and 2.
I see. So it's kind of recursive.
Exactly.
Okay.
And you can do this with regular well-founded sets.
Okay, give me an example.
Like, let's say X is the set containing the empty set, and the set containing the empty set and the empty set.
Okay, that's a mouthful.
I know, right?
But I think I get it.
So you can draw the graph for that set, and it'll be finite and have no loops.
Right, because it's well-founded.
And then you can find a decoration that gives you back the original set.
Okay, so it works for normal sets.
Yeah, but now imagine the simplest circular graph.
Okay, like just a single node pointing to itself.
Exactly, a loop.
Okay.
What set would you assign to that node?
Well, according to the rules,
Yeah.
it would have to be the set containing itself.
Right.
But that's exactly what standard set theory says is impossible.
Exactly.
So we're stuck.
Not with AFA.
Oh, what does it say?
It says every graph,
Even the loopy ones.
even the loopy ones, has a unique decoration.
So even that loop graph has a decoration.
And that decoration is the set containing itself.
That's pretty radical.
It is.
So AFA is basically saying those self-referential sets are totally fine.
Yeah, they're not paradoxes. They're just part of the system.
And those are called hypersets.
Exactly. Any set you get by decorating any graph is a hyperset.
So AFA is like this huge expansion of what we consider sets.
It's like saying, instead of avoiding self-reference,
We're going to embrace it
yeah,
and see what happens.
the whole new way of thinking about sets.
Okay, so now we have these hypersets. Some of them can be really weird and self-referential.
Right.
How do we even know when two of them are the same?
That's a good question.
Like they could look different but actually be equivalent.
And that's where B-simulation comes in.
B-simulation, okay.
It's a way to tell if 2 nodes in a graph are basically the same,
Okay,
even if they look different.
I'm intrigued.
So imagine you have a relationship between nodes in a graph.
Okay.
We call that a B-simulation.
Uh-huh.
If whenever 2 nodes are related,
Let's call them X and Y.
okay, X and Y,
Yeah.
then for every child of X,
Right.
there has to be a corresponding child of Y that's also related.
And vice versa.
Exactly.
So it's like they have the same branching structure.
Yeah. It's about matching the next steps in the graph.
I see.
And the amazing thing is,
Right.
under AFA, 2 nodes have the same decoration.
Meaning they represent the same hyperset.
Exactly.
Okay.
If and only if there's a bisimulation relating them.
So bisimulation is like the test for hyperset equality.
It's like saying 2 systems are the same.
Uh-huh.
If any interaction you can have with one, you can also have with the other.
Oh, that's a good way to put it.
And the source mentioned something surprising.
What's that?
You can actually use bisimulation to reduce hypersets to regular sets.
So even though AFA introduces all these new sets,
Yeah.
there's still the connection back to the standard set theory.
It's like you can find a well-behaved counterpart for every hyperset.
That's fascinating.
It's like saying these self-referential objects aren't completely alien.
They have a familiar side to them.
And all of this brings us to the philosophical underpinnings of these different approaches to set theory.
Right, because we've got these two very different views now,
Exactly. The source talks about the iterative conception of set.
which is the standard view, right?
Right. It's the one that supports the axiom of foundation.
Okay.
And then there's the coiterative conception.
Which goes with AFA.
Exactly. So could you explain those a bit?
Yeah, so the iterative conception is all about building sets up in stages.
Okay.
You start with the empty set,
Right?
and then you use the power set operation to get bigger and bigger sets.
Uh-huh.
And you keep doing that.
It's a very structured approach.
It's very structured, very bottom up.
Yeah, you're building from a solid foundation.
No circularity allowed.
Right.
Now, the coiterative conception is different.
Okay. How so?
It's more about sets as solutions to equations
Okay.
or as structures that come from graphs and their decorations.
So it's more top down.
Yeah. You start with the big picture,
Right.
and then you see how the pieces fit together.
And self-reference is okay.
Yeah, as long as it's consistent within the structure.
So it's a more relaxed view in a way.
It is. Yeah, it's like, okay, circularity happens.
Yeah, let's deal with it.
Let's not be afraid of it.
And AFA gives us the tools to do that.
Exactly.
Okay, so back to circular definitions.
All right.
Seems like AFA is pretty good at handling them.
Yeah, it definitely is.
How so?
Well, AFA lets us work with circular definitions of sets, streams, and trees in a very direct way.
Okay.
We don't have to immediately try to get rid of the circularity.
Right.
Like, those sets can just exist as they are.
Without having to be reduced to something else.
Exactly.
And the source also talks about greatest fixed points,
Oh, yeah.
which are kind of related to circular definitions.
Right. They're like the solutions to those circular
And
equations.
AFA guarantees they exist.
And that they're unique.
Right, so it's giving us a very powerful framework for working with these concepts.
It is. Yeah, it's really changing how we think about sets and definitions.
Now, the last part of the source gets into some pretty abstract stuff.
Oh, okay. What's that?
It talks about category theory.
Category theory. Oh, boy.
Yeah, it's a bit advanced.
But it's cool stuff.
It is.
So what does it say?
What you use is category theory to compare FA and AFA.
Okay.
And it talks about algebras and coalgebras.
Algebras and coalgebras. Okay, I'm listening.
So this might seem a bit out there,
Sure.
but it actually helps to understand the fundamental difference between those two axioms.
Okay, let's hear it.
So category theory is this really abstract way to describe math.
Right, it's like math about math.
Exactly, and a key concept is a functor.
A functor.
Yeah, you could think of it like a mapping between different mathematical worlds.
Okay.
It translates things from one world to another.
Interesting.
And then you have algebras and coalgebras.
Okay.
So an algebra is basically a way to combine things using the rules of the functor.
So it's about building things up.
Yeah, it's like putting things together.
Okay.
And a coalgebra is about how to break things down.
Or observe them.
Exactly. It's about how a structure behaves.
So algebras are about construction,
Yeah,
and coalgebras are about behavior.
right.
Okay, I think I'm following.
And then in category theory, you have these special things called initial algebras
Mm-hmm.
and final coalgebras.
Okay.
So an initial algebra is like the most basic structure of its kind.
Okay.
And you can get to any other structure of that kind from the initial algebra.
So it's like the starting point.
Exactly.
Okay.
And a final coalgebra is the opposite.
It's like the end point.
Yeah, it's the most complex structure of its kind.
And you can get to it from any other structure.
Right.
So it's like they're dual to each other.
Exactly. And here's the amazing part.
What?
The foundation axiom can be expressed as an initial algebra.
Really?
Yeah.
So it's like saying the universe of well-founded sets is the starting point for everything.
Exactly. And the anti-foundation axiom can be expressed as a final coalgebra.
So it's like saying the universe of hypersets is the end point.
Right. The most complex structure you can have.
That's incredible.
So category theory is showing us this deep connection between these two axioms.
And it's connecting it to these fundamental ideas about how we define things in math.
Exactly. Like, do we build from the bottom up or do we start with the big picture?
It's really profound.
And the source even has this chart that summarizes all these connections.
Yeah, it's like a cheat sheet for understanding FA and AF.
It links the algebraic and coalgebraic views to the iterative and coiterative conceptions.
Right.
And it even hints at connections to syntax and semantics.
Wow. So it's like these ideas are all connected.
Yeah, it's a whole web of ideas.
And it all comes back to this question of circularity.
Exactly.
All right. So I think I'm starting to get a grasp of this non-well-founded set theory.
It is a lot to take in.
It is, but it's really fascinating.
And I think it's important to remember that both ZFC and ZFA are consistent.
Right. They both work as mathematical systems.
So it's not like one is right and one is wrong.
It's more like they're different perspectives.
Exactly.
And maybe one is more useful than the other, depending on what you're trying to do.
And AFA seems to be particularly good at dealing with circularity.
Yeah, it's not afraid of it.
So here's a question to think about.
Okay.
What does it mean that we have these two different foundational systems?
That both work.
Yeah. That's a good question.
Does it mean there's no one true foundation for math?
Or maybe it means truth is relative to the system you're working in.
Something to ponder.
It is, yeah. It's a really deep philosophical question.
And maybe exploring category theory further could give us some answers.
Yeah, I think that's a good place to keep digging.
Well, this has been a really mind-bending deep dive.
It has.
Yeah.
I feel like I've learned a lot.
I have too.
And I'm still thinking about that question you asked.
That's a tough one.
It is, but it's worth thinking about.
Absolutely.
Thanks for taking me on this journey. Thanks for joining me, and until next time, keep exploring those circularities.
I will.